Alright guys, we're going to be solving another question from the chapter 4 of Engineering Mechanics by Meriam, and we have a pair of 80 Newton forces that is applied to the handles of the small eyelet squeezer, and we know that blockhead A slides with negligible friction in the slot machine in the lower part of the tool. So we're talking about this block, so it can move without any friction in this lower part, and we need to neglect the small force of the light return of the spring AE, because this is going to be in tension when the block A moves to the left, just trying to push it back to the right. So we can neglect that force as the question is telling us, and we need to find the compressive force P applied to the eyelet. So the compressive force is going to be a horizontal force that is applying to this eyelet. So it will be a force in x direction if we just call our x and y in here. And as always, we need to dismantle the squeezer in here. And what I'm going to do is that I'm going to draw the free body diagram for this part ABC. I'll just show it in here. And the forces that we're going to have, it's going to be the force that is applying from member BD. And since member BD is a two-force member, the force is going to be along the line that connects B and D. So this is going to be FBD. We're going to have the force 80 Newton that is applying on the handle. And at point A, we're going to have two component AX, AY. And technically this AX is the force or the compressive force P that is applying to the eyelet. So as long as we can find AX, we should be good to go. And what we're going to do is that the force that is applying in here is going to be this force P or the AX. All right, so we are in equilibrium. That's our assumption. So sum of all forces in X equals 0. Sum of all forces in Y equals 0. We're going to have one moment equation. We have these three equations for our equilibrium assumption. Sounds like if we can just do the moment about point A, we can get rid of all the unknowns at A, and we should be able to find FBD. And if we find FBD, the rest of that is going to be pretty easy since we have our fx equation, and we can figure AX or P out. So for doing this, since we are using our 2D shortcut for moment, we need to resolve this force into two components, and for that we're going to need to find this angle, maybe alpha, and for angle alpha we need this side and this side. That way we can find the tangent. So if we want to find the opposite side to alpha, so this is going to be our right triangle, and this side is technically 15 plus 6.25. So we're just going to put that, it's going to be 21.25. And since the line of action of the 80 Newton is going to pass through this line, so we have the adjacent side also 50 millimeter. I should show this a little bit like that. So alpha is going to be tangent inverse of this value. Let's see what we get. Tangent inverse of 21.25 divided by 50. That's going to be 23 degrees. And now that we have this, we can figure that this side is going to be FBD sine of alpha, and the other one would be FBD cosine of alpha. So let's get back to our moment equation. We're going to have the moment of the 80 Newton. This is going to be a clockwise moment, so negative 80 times. We're going to need the distance or vertical distance from A to the line of action of 80. So basically this distance, which is going to be 50 plus 62.5. So 62.5 plus 50. So that's going to be the moment of the 80 Newton force. Let's move on to the moment of the force FBD. So let's go with the horizontal component first. The horizontal component is in counterclockwise direction. So positive FBD cosine of 23 degrees. That's the force, and the distance would be, again, the vertical distance to the line of action, or this distance, basically let's just clean up the figure. So it's going to be, this is going to be our force. So we're going to need this distance, which is 15. And let's move on to the vertical component, FBD sine of 23, and that one's also counterclockwise, and we're gonna need this distance here. Again, vertical distance to the line of action, which is gonna be 62.5. And we don't need to be worried about the units in here, millimeter, because at the end, if you just want to do the unit conversion for meter, you just need to divide each of these by 1,000, and technically it won't make any difference in our equation. So we can find FBD here. So it's going to be 80 times divided by 15 cosine of 23 plus 62.5 sine of 23. So let's see what we get for FBD. So we're going to have a ratio 80 times 112.5 over 15 cosine of 23 plus 62.5 sine of 15 sine of 23. So that's going to give us 235.43, and the units are newtons, so this is going to be in newtons. And now that we have that, we're going to move on to our fx equation, and basically we have ax or p. We consider that force to the right, so ax, and we're going to have the x component of FBD, which is the cosine of 23 degrees equals 0. So our AX, which as I said, it's P, is going to be this value times cosine of 23, or 216.7 newtons. And yeah, that's going to be the final answer for this question. Hope everything was clear. Let me know if you guys have any questions. You guys take care. I'll see you in the next video. Have a good one.